Let's look at some more combinatorics problems. If you're unfamiliar with the ideas of combinations and permutations, then you should probably start with one of my other videos, which I'll link to below. To solve many combinatorics problems, though, you have to be somewhat clever in how you think about the problem. So let's look at some examples. So on this one, we'll say we have 5 men and 1 woman, and we want to know how many arrangements such that the woman is between 2 men. Okay, so that means the woman will never sit on the end. If we think of these as being 6 people in a row, it will never start with the woman or end with the woman. So how do we think about this? Well, first of all, is this a permutations problem or a combinations problem? If the men had names and we distinguished between them, so a row that started with Alex or a row that started with Ralph were treated as 2 different things, that would be a permutations problem. But I'm going to treat this as a combinations problem in which we say all the men are basically the same. So what we have is something like this. A man, maybe the woman, and then man, 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 man. So there's our 5 men. Or we might have a man, another man, a man, the woman, the man, the man. There would be another arrangement. How many different ways are there to do this such that these positions are filled by men and these positions are filled by men? Okay? So you may look at it and say, well, this is a man or a woman, this is a man or a woman, but whether or not this is a man or a woman depends on whether or not we already used up the slot with the woman, because there's only one. And same thing for here and here. That makes it difficult to really understand the problem. There's an easier way to think about this and look at it like this. So we have man, 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 man. There's our 5 men. And there's a position where the woman could sit, or there, or there, or there. If we think of it this way, we can see there's only 4 possible places for the one woman to sit, and therefore there's 4 combinations. What would it be if we thought about it in terms of the combinations formula? So we have 4 possible positions, and we're going to pick one of those. So we can say it's C41, which is 4 factorial divided by 1 factorial times 4 minus 1 factorial. This one is this one is also that one, so we're subtracting it here, which would be equal to 4 times 3 factorial over 1 factorial times 4 minus 1 is 3, so this also is 3 factorial. So these cancel, leaving us with 4 over 1, which is our 4. And then another way to think about it, and this is helpful for some types of problems, is to think about where do we move the empty slots. So there's always going to be 3 of these spaces between men that don't have a woman. So we could say, out of the 4 possible places to put an empty slot, or a womanless slot, we choose 3 of those. So that's 4 factorial divided by 3 factorial times 4 minus 3 factorial, which is 4 factorial divided by 3 factorial times 1 factorial. Well, this would be the same as this, because this was 4 factorial over 1 factorial times 3 factorial, and this is 4 factorial over 3 factorial times 1 factorial, which is still 4. Right? So regardless of which of the 3 ways, and the first one is the one that's easiest for me to think about, is that I have 4 possibilities, so there's just 4 is the answer. The others use the formula. Now what about this variation? We still have 5 men, but now we have 2 women, and we don't want the women sitting next to each other. So there's still always 1 woman between 2 men. So now it's something like this. Man, woman, man, woman, man, man, man. And then the other arrangements. And we're assuming the women are indistinguishable. So whether this is Sally and Janet or Janet and Sally, it doesn't matter. So how do we think about this? Well, we still can think about having our 4 slots But now we're placing women into two of those. So this is C of 4, 2, which is 4 factorial, divided by 2 factorial times 4 minus 2 factorial, which is 4 factorial divided by 2 factorial, 2 factorial. And 4 factorial is 4 times 3 times 2 times 1, which is 24. And that's 2, so that's a total of 4. So there's 6 combinations. Does that seem to be right? Let's look and see another way of thinking about this problem that does involve using the formula. So we have this arrangement here, and so I'm going to lock this woman in. So then we also have man, woman, man, man, woman, man, 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 woman, man, 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 woman, man. And that's as far as this second woman can move without going to the last position. All right? So there's 3 of those. And then we have man, man, woman, man, woman, man, 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 woman, man, man, woman, man. There's 2 of those. And finally, man, 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 woman, man, woman, man. And this woman can't go any farther this way. So there's 1 of those. So 1 plus 2 plus 3 is 6, which is what we have here. Now this idea actually scales. And so there's a formula that says if we go from 1 plus 2 plus dot 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 plus n, that's equal to n times n plus 1 divided by 2. So here we would have n is 3. 3 times 4, because we added the 1, divided by 2, is my 6. Remember, the women are indistinguishable here. So we're never going to have this woman continue moving across and take this woman and put her over here, because that then just replicates one of these earlier patterns, since we don't distinguish between them. So that's a possibility. So both of these, though, give me my 6. What if now, though, we said the 2 women can sit next to each other? So 5 men, 2 women. And the only restriction is women can't sit on ends. So we could have man, woman, woman, man, 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 or some other pattern. If we continue this and sort of lock in the left one, if we lock in this one, we only have 4 patterns or placements of the other woman, right, without going off the end. So there's 4 here. And if we move this over 1 like we did before, or actually, sorry, they could sit next to each other. That means there's only 3 of these. Move this over again, there would be 2, then there would be 1, right? Because finally they both start at the last slot together and not move. So using the formula we had before, that says 1 plus 2 plus 3 plus 4 is equal to 4 times 5 divided by 2, which is 10. But what is it in terms of the combinatorics formula? Because while this is true, I wouldn't want to write out all these patterns if there had been, 100 positions here. So how do we think about it? Well, now there's no longer just one slot that I can place the people in. I have 2 different slots I'm trying to keep track of. But I thought about this problem differently. Remember, these are locked in, and that means the other 3 men and the 2 women fill up the middle 5 slots. So I have man, slot, 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 man. And so out of the 5 slots, I choose 2 of those to hold the women. So this is C5, 2, which is 5 factorial divided by 2 factorial divided by, or multiplied times 5 minus 2 factorial, which is 5 times 4 times 3 factorial divided by 2 factorial. 5 minus 2 is 3, so this is 3 factorial. Those cancel, leaving 20 over 2, which is 10. So we can do it that way, and this is the scalable way, as long as you realize we're picking 2 of these 5 positions to place the women, and then the rest will just be men. And you could do like we did before, where you can say, well, pick 3 of these. In fact, we can do that. 3 of those slots to place the other men out of the 5, and then women fill the rest. So there's a 3 factorial, 2 factorial. Here it had 2 factorial, 3 factorial, so those would be the same. Here's the 5, just like we had before. So still going to be the 10. So this, I had to think about the problem a little bit differently. This one took me a while to think about it, because I still kept trying to think about empty slots and putting something. I finally realized, oh, just figure out the 2 places we're going to place the woman. Let's look at one more problem. And this would be a permutations problem. So let's say we have 4 people. We'll call them A, B, C, and D. And they're sitting around a table. Now, if they were sitting on a row, like a bench, if I said how many different arrangements are there, if we're only talking about all 4 people sitting on the row and we're talking about combinations, there's only one combination because we're using up all the people, right? But if we're talking about permutations, you could have A here, B, C, D, and A, B, D, C, and so forth. So for permutations, we would have, this ultimately would be 4 times 3 times 2 times 1, right? Which would be the 24, because that's 12 times 2. But if they're sitting around a table, things are a little bit different. If we're talking about there being like a lead chair, and this is A, B, C, D, and if we treated this differently than we would A, B, C, D, then it would still be the same, permutations. Because sitting at the top, A, B, C, D, A, B, C, D, 4 possibilities for who sits at the top of the table, followed by 3 to the next position as we go around clockwise, 2 for the next, and so forth. Then it would still be 24. But if we're talking about it in terms of who sits to the left of A, and who sits to the right of A, and who sits across from A, every one of these is really the same, right? Because I went A, and we're going around clockwise, A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. So now if we treat all these the same, really all it changes is which person's to the right, which person's to the left, and which person is across from them. Which means we really now only have 3 arrangements for those. Because I have AB, I could have had AC or AD. So it's really 3 times 2 times 1 is 6 permutations for seating order around the table if we don't distinguish between what's the top, the side here, the bottom, or the left. So either way to think about it could be correct depending on your problem. But this is one of those areas where you may think these are completely different things. And if you're just talking about who sits to my right, who sits to my left, and who sits across from me, like you're, say, playing a card game or whatever, and you don't care between this position, this, or this, then you have to realize it's not really 24 anymore. It's just a 6. So those are some examples of permutations and combinations in which you have to think about the problem more in a more clever manner, I guess, in order to figure out how to use the formula.